Yesterday when we quit, the camera had slipped and I wanted to make certain that you got all the P's and Q's of the mole concept. 6.022 times 10 to the 23rd atoms or molecules per uh, molecular mass or atomic mass. Now, an illustration of this, if you take sodium ions and chlorine ions, sodium atoms and chlorine atoms, and put them together to form sodium chloride, and you get a mole of it, it's going to weigh the atomic mass on the periodic table of sodium, which is 23, as illustrated up here, and chlorine, which is 35.5. Now, when you put them together, you might say, well, wait a minute, we got 6.022 times 10 to the 23rd atoms of each for a mole. When we put them together, shouldn't we get 12.044? No, because you change the composition. Now, instead of being a mole of atoms, it is a mole of molecules, because you formed sodium chloride, which is a compound, and thus a molecule. And it would be 6022 times 10 to the 23rd molecules of sodium chloride, 1 mole of it. So I hope that straightened it out a bit from yesterday. I don't know why the camera slips periodically, but it does. I must jar it or something. Again, this is, well, let's face it, technologically, I'm an anachronism at best. I'm a person who actually did a program on the first computer, supercomputer. It actually had a name. That's how expensive and unusual they were in those days. This is in 1971, 72, somewhere now. Yeah. At Oak Ridge National Laboratories, Pandora was the supercomputer that was being used for a radioactive study of scintillation counting. And I was charged with the, incidentally, it was 10 teletype machines and a couple of tubes that looked like nuclear bombs. I don't know whether you've ever seen a picture of an old-time nuclear weapon, but they were like 4.5, 5 foot long tubes. They were weighed a ton and a half or 2 tons, so they were gigantic chunks. Anyway, I actually pulled it off and produced something that provided a fairly decent interface between the counters and scintillation counting that they wanted to be done. And I was quite proud of myself, but that's been the extent of my computer literacy. I've spent most of the time sans computers because I don't need them. Calculators, okay, for 30 years, I could actually do most of this stuff in my head, including 3-digit numbers. But nowadays, because I'm old, I use a calculator, so sorry about that. Reality is you have a calculator, and many of you have calculators that can do everything except brush your teeth for you. And some of those may be modified for that. I don't know. Can't keep up with it. But the calculator is about as much as I ever use. So we have 23.3 plus 35.5, which gives you 58.5 grams per mole equals 6.022 times 10 to the 23rd molecules per mole. And that is the extent of our interfacing with the mole concept thus far. Next on the agenda is dilutions and stoichiometric reactions. I'm going to go through one of them reasonably briefly. I'm going to take a solution of sodium hydroxide that we're going to make up. We got 11.5 grams of sodium hydroxide. So let's erase most of this. Because we're dealing with sodium hydroxide, we're going to actually deal with hydrochloric acid in a minute. So I'm going to wipe out a little bit of this, but not much. So you got sodium hydroxide, and it's given in the problem that you have 11.5 grams. So the first thing you want to do is figure out how many moles that is. Well, sodium hydroxide, 11.5 grams. You'd have to divide it by the grams per mole. If you add this up, it comes out to be 40 grams per mole. And all you mathematical folks can figure out that the grams cancel out and moles come up top. So your answer is moles, and it's 0.288, I believe. Actually, I cheated a little bit and actually did some of this stuff in advance. Yep, 0.288 moles. Now, carrying us along a little further, they want to know what is the molarity of the solution if you divide it in, if you dissolve it in a bucket and a half of water, 1.5 liters of water. Okay, so if you take 0.288 and dissolve it by 1.5 liters, since molarity as far as solutions, you always want to know moles per liter. So when you divide that out, you'll get moles per liter, and that comes out to be 0.192. Now we use the big M, which means moles per liter. And that's the way you work all of these problems. Nothing more complicated than that. I do hope that you, what in the, I don't know, I'm having camera difficulties. Hopefully you're able to see all of that. This is a 0.1. It'll refocus. Yeah, it is. I gotta hold my hand there. It refocuses to 0.192 molar. And that should be long enough that you're able to pick it up. Okay. All right, now we're going to do dilution. Now, dilution is kind of a continuation of this whole thing. Problem I'm going to use is glacial acetic acid being diluted. Often you use glacial acetic acid because it's vinegar. Strong vinegar, but vinegar. So let's erase this and go to the next part. Dilution. All right, dilution. You have glacial acetic acid, which is 17.5 molar. That's as concentrated as it will get. And you want to 500 milliliters of 1 molar glacial. It'll no longer be glacial, it'll just be regular acetic acid. So in order to do that, you have to work out a relationship of the dilution. And you say your volume is going to be equal to the 17 point, it's not 5, it's 0.4. My bad. Started to say, I didn't recall that glacial acetic acid was 17.5. All right, so 17.4 volume is equal to the volume that you desire divided by, and what we want is 500 we want 500 milliliters of 1 molar acetic acid. So 500 milliliters is a half a liter, and that would be 0.5 moles per liter. So you take your 500 milliliters, and that becomes 0.5 moles. Divided by your 17.4, that breaks down to moles per liter. Again, your moles cancel out. You come up to the top, and I've cheated again and used a calculator, and came up with 0.287 liters. Which in real language is 28.7 milliliters. If you're in a lab, you're always dealing with milliliters, so it'd be 28.7 milliliters. And that would give you the concentration you desired, which is 500 milliliters of 1 molar acetic acid. Now, stomach acid's the same darn thing. For instance, if you wanted the same problem with stomach acid, the volume would be relatively the same, 0.5 moles, but stomach acid is not glacial acetic acid, but hydrochloric acid. And as I mentioned before, it's 6 molar in your stomach, but we'll use concentrated, which is the strongest you can get. That's 12 molar. Again, that means moles per liter. That's what this means. Divide that out, you come up with about 0.042 liters. Doesn't sound right. You come up with 0.42 liters. Yep. This will come out to be about 0.42 liters, which is 42 milliliters. That's for stomach acid. Good old hydrochloric. All right, next on the review sheet, types of chemical reactions. Now you're going to have to refer to your sheets that I gave you, the things that I told you had to learn, or at least write down so you have them as a reference point. I guess we can keep water as a bystander, but we should probably not forget the electrons that go there. So, okay, precipitate reactions are the ones that are most important when you're doing labs. And the one that everybody wants to use is silver because it makes a nice white powder. And I showed you in the lab portion how you fold the filter paper and put it in a funnel and pour the solution in, and then pour some still water back in your beaker and swirl it out and pour it in, and then pour some more and let it all drip until it's pretty dry. And then unfold the folded piece of filter paper, which again looks like a coffee filter that you use in your coffee maker, except it's round and not wrinkled like your coffee filter is. You have to do the wrinkling when you fold it. Then you dry it. You will have weighed the filter paper prior to the experiment and weighted it again when it's dried. Subtract those, and that would be the amount of in grams of the silver chloride that you produce. The reaction is most often used is silver nitrate, which is aqueous, means it's dissolved, obviously, plus, some of the column 2s or column 1s, depends on, I guess column 1s is good enough. So we use potassium chloride. Now, because electronegativity differences, the silver wants to go to the chlorine because then it becomes, this is aqueous also. The silver goes to the chlorine where it's no longer dissolved, becomes a solid. And the potassium jumps on board with the potassium, with the nitrate, to become potassium nitrate, and stays aqueous. This is your solid. This is what the white powder that comes out of the reaction that you filter out. And this is a classic lab experiment for general chemistry, first semester. And you should, in fact, probably have that. And again, there's quite a few other precipitant reactions. I strongly suggest that you get your chemistry book, whatever one you bought, a used chemistry book. For Pete's sakes, there's a lot of them out there. And they're not expensive. This textbook business is a racket. It always has been. The only one I've found over the decades that was worth, even close to worth the money, was Zumdahl's books. Most universities, okay, I'm not giving up any secrets here. They got their own little moneymaker. They get a professorial member in the chemistry department to write a textbook, generally a paperback, and they charge you bodacious amounts of money. They kick back to the professor a small amount, but the bookstore makes most. And same with a lab book. So my suggestion of getting a used textbook will come to your advantage. Because 10, 15 years ago, doggone textbooks were really complete. And you got twice as much material as you actually needed in the course. Or in today's course anyway. I mean, I would venture to say that if you can master a good half of what Zumdahl puts in his general chemistry book 25 years ago, you'll ace out Gen Chem in any school in this country. Sorry, I'm aware of how good, bad, or indifferent they are. All right, enough of my critiques of the universities in this country and the colleges. I don't think they push it hard enough. So that's just me. Now, the next type of reaction we're going to talk about is acid-base. And since I'm an old fuddy-duddy, I'm going to stick on sodium hydroxide and hydrochloric acid. And the reason for that is it becomes really familiar after you use it a few times, and it's like second nature. And the substance produced in this reaction is something that you're made of, salt. You're partially made of salt. So the problem is, the question asks, what is the volume of 0.1 molar hydrochloric acid needed to neutralize 25 milliliters of 0.350 molar sodium hydroxide? Now, you know the reaction. It's And we'd say this would be aqueous. This would be aqueous. The sodium chloride can be evaporated out. The water can be evaporated out of it, so you might call this a solid, even though it actually stays pretty much in the solution. So the problem is 25 milliliters of this. Times the concentration of it. Now, we don't deal in milliliters, mostly we deal in liters. So you multiply it times 1 liter per 1,000 milliliters, which is conversion factor of the two things. And then whatever you get, you multiply it by the 0.350 moles of the hydroxide, same as the sodium hydroxide, divided by the liters of NaOH. So I'll give you the moles of the NaOH, which comes out to be 8.75 times 10 to the minus 3 moles. Now, all you got to do to get a neutralization of that is find out how much of the 0.1 molar hydrochloric acid is necessary to produce 8.75 moles. And believe it or not, it's not actually rocket science, because the hydroxide and the hydrogen ions are 1-to-1. I mean, when you form water, it's H plus OH minus for HOH, or water. So all of you can do that. So when you're setting up the problem, you get the 8.75 times 10 to the minus third moles of the hydroxide ion that you want to neutralize, and you would divide this by the 0.1 molar hydrogen ion, because it's the same. In other words, you want the same number of moles of the hydrogen ion as you have the hydroxide, because they're a 1-to-1 ratio. In other words, they neutralize each other 1-to-1. So to change this, take 8.75 times 10 to the minus third moles of the hydrogen ion divided by the 0.1 molar solution, which is given to you in the problem, per liter. And it comes out to 8.75 times 10 to the minus third liters of acid. Or for all you sticklers, you can change that to milliliters by multiplying by 1,000. And that's our acid-base neutralization problem. In other words, this is 87.5 milliliters of 0.1 molar acid to neutralize the 25 milliliters of sodium hydroxide. Straightforward problem, not particularly difficult. Hopefully you comprehend what I'm trying to get across. And that will be the review of the day. Next time we're going to be doing that favorite of everyone, oxidation reduction. And that'll be the last of the review. So hopefully you will have finished the first 22% of the course.